Morning. Today's introduction is in interrupts. Purpose is just to give you a very light understanding of what it is about. Understand that this is normally a 3-hour topic, so all I can do in this 15 or 20 minutes is just touch on the topic. But it'll give you a good basic foundation that you can lay further discussions upon. So, the interrupts that we're going to be talking about are for the 84 Alpha PIC microcontroller. What is an interrupt, first of all? Well, let's look at it several. Basically, it's some kind of an external event, or perhaps internal, which is going to stop the normal program flow to have the microcontroller go and look at what is happening. Take, for instance, say you have the microcontroller is asleep and you want to wake it up every once in a while to look around, see what is going on. Is there a reason to stay awake? If not, then go back to sleep. If it is, then perform what action is required and go back to sleep. This saves on power, saves on batteries, etc. So we would have something called the watchdog timer, which is running while it's asleep, is not dependent on the actual internal timers. It's separately controlled, and it uses very little energy while it's running. And that timer, watchdog timer, would time out. The interrupt would be generated. The system would wake up, look around, do what's necessary, and go back to sleep. Take another example. Suppose the microcontroller is in charge of controlling the movement of a robot. Now, this robot is probably going to have sensors on the front and the back and the sides. And as long as there's nothing in the way of these sensors, the microcontroller is going to just have the robot moving along the line, doing however it's supposed to be controlled via a path it's supposed to follow, or GPS, or so on. However, when one of the sensors senses a blockage, a interrupt would be created, and the microcontroller would cease that program operation. Now, remember, this is a very fast operation, so you might not even notice it in the actual slowing of the robot. It would go figure out which sensor it was, figure out which direction to turn, and then slightly turn it, go back to main program. If it wasn't enough, another interrupt would occur, go back in, turn it a little bit more, etc., until finally it has passed it, the obstruction, and it will start to turn back and get back to its original path, however that is done. Interrupts are basically, in my mind and heart, are truly what makes a microcontroller powerful. Two types of interrupts. One is the maskable type. This interrupt cannot be ignored by the controller. Excuse me, can be ignored. It can be ignored by controller. We can turn them off if we want. And non-maskable, it can't be ignored. Among other things, this type of interrupt cannot be affected by the global interrupt enable bit. So even if the interrupts are not enabled, this particular interrupt is not affected by that bit. There are four sources of maskable interrupts. The first source would be an external RB0. Now we can set that as determine which edge of that we're going to have it cause the interrupt. This is on the RB0/INT pin. Now this is basically a dual purpose pin. It can be a RB0 input or output, or it can be the source of this interrupt. Timer 0 overflow. Now there is a timer 0 inside the device, and it can either be counting internal clock pulses, which is with the internal method, or it can be counting the pulses that would be on RA4 if it's set that way, which would be external overflow. And then when the timer 0 overflows, a interrupt would be generated. We also have a condition of setting it so that if there is a change of state level, meaning a 0 to 1 or 1 to 0, on port B pin 7, 6, 5, or 4, that this would cause an interrupt. And finally, there is an interrupt that says the EEPROM has finished writing its data to itself, and now it's time to close down the EEPROM so it can't be written to anymore. The two sources of non-maskable interrupt, well, one was that watchdog timer interrupt that we talked about. Another one would be the reset button. There is a reset pin on the microcontroller, and when we reset the device, we want it to stop operation, and we want it to send the program control, i.e., we're going to place the reset vector 0x0000 into the program counter, which will then cause it to start operation again at that reset vector. This is all instigated by the Global Interrupt Enable bit, the GIE. Now, this again only controls those 4 maskable interrupts, and this bit is bit 7 in the INCON register, and it must be set to enable interrupts to be able to occur. Now, we still have to be able to enable the actual interrupts themselves, because we might not want all of them running at the same time. All right, but that's how we do it. Now, when the interrupt occurs, this GIE is cleared by the hardware interrupt handler, which we'll talk about in a bit, which will keep further interrupts from affecting the system until the GIE is set again when it returns from servicing whatever interrupt it was working with. Note that even though the GIE is cleared during the servicing of the interrupt, other interrupts are still occurring. They're just not affecting the system. Even though they do not actually interrupt the system yet, the flag for that interruption is raised, and when the GIE is set again, the system will note the raised flag and a new interrupt process will occur. Now, one of the problems here is we need to keep our interrupt service routines fairly small, because while the routine is running, the system is basically interrupt blind, meaning it's going to be a while before the interrupt gets serviced, and some interrupts might be more important to happen immediately than others, so we need to keep the service routines fairly short. Now, we will continue to have this back and forth action happening until when the GIE is set and after returning from servicing the interrupt and there are no further interrupt flags raised, then it can go back to the normal operation of the program. Now, this is the INCON register. Note that the bit 7 is, as we talked about, that's the global interrupt enable. 0 disables all interrupts. 1 enables all maskable interrupts. But that doesn't mean that they're all interrupt. It basically makes them possible to be enabled. Basically, is more likely to affect the system. Now here are the 4 enable bits, bits 6, 5, 4, and 3, which basically will enable each of the interrupts. that are maskable. Again, 0 disables the interrupt, 1 enables the interrupt. And finally, here are the flags. Now notice there's just 3 of them showing here. The 4th one, the double E write complete interrupt, has a flag that's associated, I believe, as an EECON 1. Alright, not in this one. Note that each one of these flags are cleared by software, meaning we must be doing the programming. That's part of what has to happen during the service routine. Now, where is this ISR, this interrupt service routine, placed? Well, there is, first off, when you take a look at how we're in program memory, the reset vector is 0, 0, 0, 0. The interrupt vector is at 0, 0, 0, 4. Any interrupt service routine is placed here, or a go-to to it, that ISR is placed there. Now, we don't want the normal program operation, which starts at 0, 0, 0, to actually run over this ISR, so we must have a go-to label, for instance, a go-to start just before this address, 0, 0, 0, 4, which is going to cause it to jump over this period and go to the label that we want to go to, for instance, to the start label. Note that the interrupts are not going to be used. There is nothing wrong with using this program memory space for the main program code. So obviously we would not have a go-to label then. The hardware stack. There are 2 event conditions which use the hardware stack: subroutines and interrupts. When either of these conditions occur, the current command being executed is completed. The address of the next instruction, which would have been executed if it hadn't been for the event or condition causing this, is then pushed to the stack. And then the address of the subroutine or the interrupt, meaning this interrupt address would be 0004, is placed into the program counter and execution continues. This is all done automatically. We don't have to do anything as a programmer. When the subroutine or ISR is completed, the top address on the stack is popped from the stack back into the program counter. Remember that this address was the next instruction that would have been executed, so basically that causes execution to take up where it left off and continue normally. Now, with this level of PIC, the hardware stack is limited to 8 levels. Now, this kind of stack is a LIFO stack, meaning last in, first out stack. So basically, we shove stuff in, and then previous ones get pushed down. And then if it goes too far, if we go past the 8 levels, the original first one in that was put in at the beginning is shoved out the bottom, and it is lost for all time. What would happen there is when finally everything gets popped and we're looking for that very first address, it won't be there and the system is going to basically get lost. Now, it is very good programming practice to have the number of stack levels used by a subroutine, including ISRs, to be listed inside the subroutine header. This number of stack levels should be the total, including the subroutine itself. You got to remember that sometimes subroutines call other subroutines. It's called nested subroutines. So an ISR will be using subroutines, and at any time a maximum one of those subroutines will be in the process of being executed. The header would indicate 2 stack levels, including itself. Now, the hardware interrupt handler is going to, when the interrupt is triggered, the handler will clear the GI bit, set the appropriate interrupt flag. Now, it's going to also continue to set the interrupt flags even when the GIE is cleared. Whenever an interrupt occurs, it will set it. It just won't affect the system as long as the GIE is cleared. We're going to push the contents of the program counter to the stack. We're going to load the interrupt vector, which is 0004, into the PC. And that will cause the interrupt routine to start running. Once the ISR has been serviced, okay, the hardware interrupt will pop the instruction located address located at the top of the stack to the PC, not the instruction but its address, and which will then return operation back to the main program and then set the GI bit in the incon register. All the requirements for proper interrupt handling, such as saving and retrieving registers without having them being corrupted, flag clearing, interrupt prioritization, anything else, is responsibility of the programmer writing the ISR, not hardware. So here are the programmer's obligations. When an interrupt occurs, a programmer is obligated to ensure the following items are included in the code. First off, we need to worry about the 2 most important registers that were being used by the main program, which was the W register and the status registers. These registers are going to be affected by the ISR. There's almost no way to prevent that. So we want to be able to have a way to protect the contents of these so that when we are finished with the ISR, we return these contents back to the main program unchanged. So we have to find a way to save these 2 registers without corrupting their contents. And we'll look at that in a bit. We need to determine the source of the interrupt. Now, the method of determining that source is going to determine the prioritization of those interrupts. So the first one we look for is going to be the most important of the interrupts. We're going to service the interrupt. Then we're going to clear the corresponding interrupt flag. Remembering it was set by the GIE, we are responsible for clearing it. And these flags are either, the 3 of them are in the incon register and 1 of them is in the EECON1 register. Then we're going to perform a retby command. That's return from internet interrupt. Now, it's also important to note that there's an additional thing that has to be done within the ISR if the interrupt was a change of state on port B, pins 7 through 4. We have to perform a dummy read on the port pin which had the change of state performed on it. The reason is there is a latch on these pins that is in effect that will have that level there, and even if we were to change that level on the pin, the latch is going to stay there. So we have to perform a dummy read on that to be able to clear the mismatch from what is on the latch and what is actually on the pin. Now the push routine. First thing we're going to do is we're going to use the move WF to a register called WSAV. Okay, so it's protected for now. Then what we're going to do is we're going to take status and we're going to swap the lower nibble, remember a nibble is 4 bits, with the higher nibble, and we're going to put it in the W register. Okay, and then we're going to move that value to status save. Now the interesting thing about swap F is it does not affect the status register. It's one of the very few commands that does not affect the status register. Now it should be noted here, I've written this particular routine as a subroutine. Okay, in general this is not a good idea because it's using up a stack level. But if you've written a program that is not necessary to worry about the stack level because we're not going to be nesting too many of them, and we're not worried about using the clock cycles that are used because of a subroutine, then this is not a bad way to go. I've shown the actual commented code below this section, although I'm not sure you'd be able to see it on your screen. It's in the handout. Pot routine. This is a really interesting routine. Remember again that swap F does not affect the status register. So what we're going to do here is we're going to use the swap F command to get it into the W register. Okay, what we're going to be doing here is we're going to now, remember we had swapped the status register and put it in the status save. Now we're going to swap it again, bring the lower and upper nibbles back to their correct positions, and put it in the W register. And then we're going to move that to the status register. Remember, move WF does not affect the status register either. Now we need to get the W register back into it. Now here we're going to use two swap Fs. The reason why we're doing this is that we don't want to affect the status register. So swap F, WSAV, comma F. We're going to basically swap the two nibbles. Remember, we didn't swap WSAV before. So now we're going to swap it, put it back in WSAV, and we're going to swap it again and put it in W, and we're doing this now without affecting the status register. Very ingenious, I think. I didn't write this. This is a standard routine. And finally, what happens if the program is not in bank 0 when the interrupt occurs? Well, as a matter of safe programming techniques, the ISR should, as a matter of course, ensure that it is in bank 0 while operating, just in case the program was in bank 1 when the interrupt occurred. Okay, so one of the things you should probably do in the ISR is shift to bank 0. When we restore the contents of the status register after the ISR, this will cause the program to shift back to whatever bank it was pre-ISR. So we're right back where we started from. And that completes our introduction for the interrupt service. Now remember again that this is a very long subject, so you're not expected to understand it after this short introduction. We will continue during a longer lecture later. Thank you.